Good afternoon, everyone. My name is Austin Crow, and I'll be going over a paper focused on VRSANet. The title of this article is VRSANet, VR Sickness Assessment Considering Exceptional Motion for 360-degree VR Video, authored by Kim, Lim, Lee, and Rowe. Rowe is actually a senior member for IEEE, which only gives more credit to this article. The student Kim, Lim, and Lee all studied at universities in South Korea. At the time of this article, Kim was pursuing a PhD, Lim was pursuing his master's degree, and Lee was pursuing a joint MS-PhD degree. Let's take a look at what the problem this article is addressing. The major focus is that virtual reality often leads to motion sickness of the users. The motion sickness takes away much of the benefit that virtual reality can bring, whether it be for entertainment or learning. This motion sickness is broken down into three primary categories, with the first being ocular, followed by disorientation and nausea. Ocular symptoms are usually along the lines of visual fatigue and difficulty focusing. The disorientation symptoms are oftentimes more severe and come in the form of dizziness and vertigo. Lastly, we have nausea, which consists of sweating, salivation, and burping. While each of the symptoms are manageable on their own, they become much more exaggerated when they start piling on top of one another. This motion sickness is not something that affects a small minority of people, as 80 to 90% of people report some level of VR sickness, myself included. Virtual reality has become an ever-growing section of the technology industry, getting introduced into all forms of business and entertainment. With the rise of Oculus Rift, HTC Vive, and many more, private consumers can enjoy the luxuries that VR has to offer in the form of video games and simulators, giving the users a deeper dive into their entertainment. Outside of the entertainment, many businesses are using the power VR has to offer in order to help their employees or those they're training learn faster and easier. A great example of this is pilots can use VR to fully immerse themselves in what it would be like to fly a plane or helicopter without running the risk of actually being in one of those aircraft. In the standard workplace, VR has been known to reduce staff training time by up to 60%. Also, in this training, VR can be used to safely simulate what a hazardous or dangerous situation would be like without the employee being put at any risk. The term three-dimensional convolutional neural network is going to come up quite often throughout this presentation, so I'd like to give a high-level overview of what it is. A 3D convolutional neural network is made up of three kinds of layers, these being convolutional, pooling, and fully connected layers. The network also has three properties: local connectivity of hidden units, parameter sharing, and the use of pooling operations. A hidden layer is unique in that it is not connected to all the previous layer's units, but only a small amount of spatially localized area. This helps with non-overfitting by an excess amount of parameters. This is also helpful when looking at images, as it can find localized features easier. The hidden layers are then connected via feature map. These feature maps are useful in keeping the number of properties down, as all layers on a feature map share the same properties. The convolutional layer is made up of many of these feature maps. The convolutional layers are what find the patterns and features in a three-dimensional image. The convolutional layers are then followed by the pooling layers, which get rid of some of the hidden layers in order to build robustness. The feature maps are then pooled together, and this serves as an input for the final layer, which is the fully connected layer, thus completing the 3D convolutional neural network. The authors made sure to look into related work that would be beneficial for their study. With these related works, they were able to get a jump start on their model. The first looked into image quality assessment and looked through many variations of peak signal-to-noise ratio, where they decided that the weighted to spherically uniform PSNR and the Craster parabolic projection-based PSNR were the best. They also looked into deep learning-based VR image quality assessment, where an adversarial learning was employed to assess the performance of a degraded VR image and how it could be improved. The authors also used VR sickness assessments, where they looked at cyber sickness and how it correlates to physiological changes, such as measuring the electrophysiological signals. This had a positive correlation showing that VR sickness changes activity in the central and autonomic nervous systems. Many commonly used tests are very cumbersome, and the authors strove to find a way to get rid of these cumbersome methods. Lastly, the authors looked at deep learning for visual quality assessment. Recently, a deep learning method for 2D and 3D image quality assessment was proposed for prediction accuracy by modeling human visual perception. The majority of the models looked to work off the convolutional neural network, which ended up being what the proposed model used. The method overview can be understood simply via this graphic. The proposed method is broken up into two main parts. These two parts will be focused on more in depth as the presentation continues. The first part is the video generator, as can be seen in section A of the graphic. The second is the score predictor shown in section B. As shown in section A, the generator takes from a database of VR videos with non-exceptional motion, then generates VR videos with non-exceptional motion. In section B, videos of varying levels of motion are both sent to the now trained generator as well as directly into the predictor. The various video motions that are sent to the trained generator are then converted into newly generated VR video, and is pushed through the score predictor. This score predictor takes these various VR videos and outputs a VR sickness score. Before we jump into a more in-depth look, let me explain the difference between exceptional motion and non-exceptional motion, as these terms will be used quite frequently. Non-exceptional motion is the motion that we are used to in our day-to-day lives. Slow and normal movement, such as walking or casual driving. The opposite is the case when looking at exceptional motion. This is something that would be well above your average movement, such as a roller coaster, Formula One, or NASCAR racing. Let us take a deeper look into the generator. The learning is done via unsupervised learning by looking at the spatiotemporal characteristics of normal videos with non-exceptional motion pattern. This is done in hopes to learn the motion sickness tolerance level of human perception. By combining the convolutional neural network and the convolutional long-term short-term neural network and the spatiotemporal discriminator of the three-dimensional convolutional neural network in an adversarial way, it is not only generated by the autoencoder, but also refined to be similar to the characteristics of normal video with non-exceptional motion. To put this in a more understandable way, the generator takes spatial characteristics and encodes them with the convolutional network, then the temporal characteristics with the LSTM, then with the LSTM again decodes the temporal characteristics, finally going back to the convolutional network to decode the spatial characteristics. This generator does very well reconstructing videos when it comes to non-exceptional motion. However, when it comes to videos that have exceptional motion that go over the tolerance level, the generator does not recreate well. By adversarial learning between the generator and the discriminator, the generator in the methodology can synthesize a realistic video with a normal range of motion. The predictor is used in order to automatically determine the VR sickness score. This is done by comparing the generated and original videos and finding the difference between the two. The subjective sickness score then has that difference mapped onto it, which can then reliably predict the subjective score. The error created via the reconstruction of the generated VR video represents the exceptional motion. This error can thus show what is causing the VR sickness. The proposed predictor, shown on screen, works by using a small set of VR sickness datasets, and it can still reliably predict the sickness score. This is directly compared to the conventional network architecture, being the three-dimensional convolutional neural network, which historically needs a vast dataset in order to be accurate. The predictor looks at the difference between the original video and the generated video. This difference then is used to determine the exceptional motion that could lead to VR sickness. The three-dimensional convolutional neural network, shown in the graphic, is used for encoding spatiotemporal characteristics of a sequence of the difference maps. Spatiotemporal refers to the time and location of a given situation or occurrence. The difference map from the VR generator learning normal motion perception is mapped to the human subjective score space. In training, the score is predicted by minimizing the loss between the ground truth, which in this case was the subject-created VR sickness score, and the predicted score. When testing, the difference maps are obtained by trained VR video generator. Then with the sequence of difference maps, the final VR sickness score is yielded by the VR sickness score predictor. The architecture of the spatiotemporal discriminator is 5 three-dimensional convolutional layers followed by a 64D fully connected layer. The simulated sickness questionnaire, also known as the SSQ, is a subjective way to measure the effects of VR sickness on a person. This SSQ is subjective because it is given to a subject after they've gone through the test to determine how they felt regarding sickness based on a set of criteria. The SSQ is considered to be the ground truth as there is no automation going into it. It is the actual response of the subjects. Due to this, the SSQ is used in order for the predictor to learn. Any SSQ with a score of less than 28 is considered to be a non-exceptional motion, such as looking through scenery or normal driving. However, any score that is greater than 40 is considered to be exceptional motion, and these are the fast-paced videos such as roller coasters or extreme driving. The scores of 28 to 40 are in the middle gray area, where the videos begin to transition between non-exceptional to exceptional. The generator mentioned previously is trained based on the videos that have a score less than 28. This is done by minimizing the SSQ score and the predicted score. This graphic shows an example of the 16-item SSQ that was given to the subjects. The subjects were given 150 seconds in between each video to determine what their symptoms were. These 16 physical symptoms were determined to be highly related to VR sickness. The items are ranked on a 4-point grading scale, from 0 being none, 1 being slight, 2 being moderate, and lastly 3 being severe. Each of the items have 3 categories, these being the 3 main subsections of VR sickness mentioned earlier: nausea, oculomotor, and disorientation. The nausea features consist of general discomfort, increased salivation, sweating, difficulty concentrating, stomach awareness, and burping. The oculomotion features are fatigue, headache, eye strain, difficulty focusing, and blurred vision. Lastly, the disorientation features are fullness of the head, dizziness with eyes open and closed, and vertigo. This grading scale shows just how subjective the SSQ is, and because of the subjectivity of the matter, it is important to have a large number of tests. The graph shows the 9 videos presented to the subjects and how they ranked compared to one another. The y-axis represents the SSQ scores, while the x-axis shows which number video. Green represents oculomotor, nausea is blue, disorientation is yellow, and finally red is the total score. It is important to know that each of the categories are not equal, as there is a weight associated with each. These weights being 7.58 for oculomotor, 9.54 for nausea, and 13.92 for disorientation. The scores are determined by getting the summation of each of the SSQ items in their respective categories, multiplied by their previously mentioned weights. The graphic gives a great visual on what category is most apparent and what causes the most motion sickness. Oculomotor often is the least impactful feature and thus seems to be the least decisive feature when it comes to VR sickness. Constantly, disorientation seems to be the feature that causes the most VR sickness, as in the first 6 videos that would represent simple and normal movements, the disorientation is about average with the rest of the features. However, when looking at the last 3 videos that represent complex motion, the disorientation skyrockets, drastically outshining the other 2 features of ocular motion and nausea. Something to look at is the video number 3, as it appears to be more akin to videos 4 through 6, rather than the previous 2, and we can take a look at that in the following slide. The dataset used in the previous graphic is shown on screen now, and to give us a better understanding of what was actually being looked at and why those values were what they were. The motion is broken up into simple, normal, and complex. We can see that the first set of videos is primarily low motion, looking around a landscape. However, video number 3 is cockpit flying in 360 degrees. This would explain why previously it had a higher degree of VR sickness when compared to videos such as surrounded by wild elephants. The normal videos are primarily driving videos with a wingsuit video thrown in. The last set of videos are interesting as they are considered to be complex motion and are the Superman roller coaster, which is known to be incredibly fast, rally car racing, which is another high-intensity visual stimulation, and lastly jet racing, as jets are known for their speed and quick movements. This would explain why the correlated score were so much higher than the previous videos. Some other things to look at on the dataset is the resolution quality. The videos are in high resolution in order to help with the authentic feel, as well as an average FPS of around 30. Lastly, each clip was 90 seconds long to stay uniform amongst the data. Let's take a look at some of the logistics involved for this experiment. The head-mounted display used was the Oculus Rift CV1. The VRSA framework was implemented using TensorFlow, and the datasets used for training the video generator were the KITTI benchmark datasets and content from Vimeo. The KITTI datasets consisted of 61 normal driving videos, being city, residential, and road. 20 non-exceptional motion videos were from Vimeo. The VR sickness predictor was trained by another 21 videos in order to set a ground truth. In total, there were 60,746 frames used in order to train the video generator. For the VR sickness predictor, 20 additional subjects were tested using the same SSQ as previously discussed. The performance of the model was based on commonly used performance metrics in Pearson linear correlation coefficient, Spearman rank order correlation coefficient, and root mean square error. 6 objective metrics were compared, including the proposed VRSA-net, 3 of which were physiologically based signal methods, these being heart rate variability, and galvanic skin response. The difference between heart rate and heart rate variability is that heart rate looks at the mean heart rate at a given time, while the heart rate variability looks at the standard deviation of the heart rate in that given time. The optical flow method looks at the average magnitude of the optical flow, which is the motion information from the videos. The deep learning approach uses a three-dimensional convolutional neural network, which is one of the main architectures for video analysis. Outlined in red, you can see the scores of the proposed method. As you can see, the proposed method scores significantly better in all categories, with the next closest being the optical flow-based method. This shows that the VRSA-net has a strong correlation with the subjective VR sickness scores. This also shows there is a correlation between heart rate variability as well as the galvanic skin response to the VR sickness, while the heart rate method did not have a significant correlation. As seen previously, the proposed model scored the highest in all tests, showing that there is a strong correlation between the model and the VR sickness scores. Thus, compared to the models tested, the VRSA-net achieved a better prediction performance. This also shows that the motion mismatch of virtual reality compared to real world is among the most important factors when looking at VR sickness. The proposed model could also be a great time-saving achievement, as the VRSA method could produce a VR sickness prediction without the need of cumbersome physiological signal measurement. While the generator does great when looking at videos without exceptional motion, it does not do very well when looking at videos that do contain exceptional motion. This is likely due to the generator being trained on a non-exceptional motion video dataset. The two figures on screen show a visualization of what areas most affected the VR sickness prediction. These are some examples of the VR reconstruction by the proposed generator for videos 1 and 7, the wild elephants and Superman roller coaster respectively. As the proposed model cannot move its head around like a person can, the videos are broken up into normal field of views, also known as an NFOV. The first row represents the video's original normal field of view, while the second row represents the normal field of view created by the generator. The third and final row represents the normalized reconstruction error maps. The dark blue represents that there is no error, while the red represents a high amount of error. To the naked eye, the frames may look almost identical, but the method sees a clear difference. Looking at the graphic with the elephants, the error map looks like it's a completely blue square, thus resulting in a low VR sickness rating. Juxtaposed to this, we have the roller coaster's frames, where it is much easier to see the difference in the third row with lighter shades of blue and yellow. It is important to notice that these discrepancies are around the fast-moving parts of the image, and in this case, it's the track. These differences let the predictor know that this video has a particularly high amount of exceptional motion. Like all projects, there are some limitations, things the authors wish they could have done, and future works. One of these major limitations is the variability that comes with people testing. People vary in levels of health. In the case of this project, all subjects were healthy, while in life, those that may not be in the best health could react to videos very differently. Along with the health, there is the factor of age. Those in the assessment were between the ages of 20 and 30. Children 12 and under have not developed their visual vestibular sensors and thus should not be exposed to an excessive amount of VR, while those who are older tend to have ocular motor dysfunction, leading to a higher severeness level of VR sickness. Also, more than 20 subjects could only be a benefit. When it comes to future work, it would make sense to investigate more causes or features for VR sickness. In conclusion, the authors proposed a model that used a generalized activity network to learn the tolerance of VR sickness in human motion perception rather than end-to-end training of a regression model with a large number of VR datasets and a corresponding subjective scores. The proposed VRSA network quantifies the degree of VR sickness, and it can detect the area where VR sickness is caused, thus showing that exceptional motion is highly related to the level of sickness. By using a subjective questionnaire, a baseline was created for the predictor to learn from. The generator takes a normal field of view frame from the 360-degree virtual reality video and creates a new frame. By using the error between the original and generated frame, a score is given via the predictor, and the user can see what level of VR sickness the video may have. The use cases that this project could be adopted to are as vast as the uses for VR. One of the main problems with VR in its current iteration is that it makes people feel ill, and if the users feel ill, they are likely not to want to continue using the product. This model would be great if introduced into game design. With proper implementation, developers would be able to figure out what in their game works for people and what would make their player base want to give up the game. Pilot training is another great example. Simulators are a great way for people to feel like they're flying or driving from the comfort of their house. By using the sickness predictor, military pilots could figure out what they are able to handle before they are put in the cockpit of a plane. Drone videos are very popular, especially when looking to give a tour of an area or get a better view of something. With this model, optimizations can be made to help users from feeling ill. When thinking about project ideas, this paper was a great resource for me. The idea of VR sickness is something I would very much like to continue to look into, as I tend to get fairly motion sick playing certain games. I personally start to feel ill moving around in games, particularly backwards or in a direction I am not looking. A project idea that I would like to look into is research and ranking into what movement methodologies produce the most motion sickness. For example, the two most common movement methodologies I have seen are using the joystick on a handheld controller to move the player and using the controller to point at a specific location and teleporting to that location. After the ranking is complete, I would like to look at characteristics that are more favorable amongst the methodologies and try to enhance a current methodology or develop a new way of movement with motion sickness in mind. Another project idea is looking into ways to counteract the effects of motion sickness in VR. This article focuses on finding if a video can or will cause motion sickness. The logical next step would be to figure out how to stop that video from making the viewer ill. Likely, one of the solutions to look into would be getting the body more involved. A major reason for VR sickness is the disconnect from what you are seeing and hearing compared to what the body is actually doing. Thus, by a higher level of incorporation of the body, one's level of sickness may be reduced. Now, I would like to thank everyone for your time.